Hi, we're the University of Iowa Robotics Club, and we're proud to present our 2018 Mars rover. In previous years, we were part of the NASA Robotics mining competition, and recently we switched over to the URC. From those experiences of last year, we have learned the challenges that come in and completely overhauled our administration, project management, and manufacturing styles to accompany the challenges that the URC provides. In order to keep our parts economical, we utilize standard manufacturing processes for basic geometries of load-bearing devices, and then combine that with additive manufacturing for the complex geometries.
We reuse the successful in-wheel motor mounts from last year's rover and redesign the rest of the frame from the ground up. The main chassis uses 80/20 aluminum extrusion, and the rest of the frame is custom fabricated components. We opted for a swerve drive mechanism this year to allow for increased agility and reduce the turning loads on the rover. Each hub is independently driven by a stepper motor installed within the suspension arm. The suspension arms are connected to the frame through a differential bar, also fabricated by us, and allows the rover to traverse large obstacles with ease.
To be successful at both the extreme retrieval and equipment servicing tasks, we designed the 5-degree freedom arm with several key features. The first one is our gripper. We picked an off-the-shelf gripper that fits our design. Our wrist motion is achieved by a beveled differential gear system that is powered by 2 planetary gear stepper motors. This allows us to get 2 degrees of freedom, both translation and rotation on the hand. Our frame design for the arm was driven by a ridge bubble to make sure the arm has enough motion and can touch the ground. We also included a swappable forearm so we can complete both these tasks and the science kaizen easily. All the components will be powered by inverse kinematics to achieve both precision and smoothness in controlling them. And our industry advisor from Whirlpool is guiding us through that process.
The drill functions via a combination of a feedback meter actuator and a standard drill motor. The feedback allows us to keep track of the depth that we're going into the ground, and the motor has an auger-style drill bit attached to it that allows us to collect and rise the dirt into our collection and analysis system. In our onboard analysis system, we will be utilizing a microscope as well as a temperature and humidity sensor. We will also be running a UV analysis and determining the capacitance and resistance of the soil that we are collecting. And while we are running this analysis, we will be controlling what we are dumping versus collecting through the usage of a actuating latch in our collection system.
As part of our science caching equipment, we'll include a weather station complete with sensors for temperature, humidity, pressure, UV index, wind speed, and wind direction. As part of our in-lab tests, we'll include pH tests, soil fertility tests, various mineral and biological tests, as well as compound light microscopy.
We are using C, C++, and Python in an Intel NUC that sends commands to various Arduinos. Then the Arduinos control the motor controllers. An interesting thing about our team is how we recognize tennis balls. Instead of using algorithmic-based recognition, we use machine learning via Caffe and NVIDIA, open source NVIDIA library.
We have several FCC licensed members that develop 3 distinct communication protocols. The first communication protocol is over the 2-meter band for utilizing Baofeng's and slow data connection. Our secondary communication protocol is over the 900 MHz band for RC control. And finally, we are utilizing amateur television protocols over an SDR for video streaming. This system, coupled with a base station antenna that follows the rover's GPS bearings, allows for robust communications. To prepare for the competition, we will put all components under rigorous testing and analysis. To date, this has included FEA models, theoretical calculations, variable environment driving tests. We will also train on the arm using a playboard and outdoor tests. The drill will be exposed to various soil environments, and the control systems and autonomy will undergo simulated URC tasks. All of our systems will be pushed to their limits so we can address issues now rather than in the desert.